Okay, hi. My name is Ashwin. I'm from Duke University. You don't need to know my last name unless you take a course with me. All right. I plan to talk about differential privacy and relational databases and sort of a case study on census data. My colleague and collaborator Michael Hay was actually going to talk about something else, which was sort of facilitating design and evaluation of differential priority algorithms. He's not around here, so then Adam said maybe you can talk a little bit of both. But given my 25-minute time constraint, I'm going to see what I can try do in this time. Okay. All right. So this is the standard preamble. There's aggregated personal data everywhere in many different forms in many different domains. But then if you just sort of do it in some naive fashion, privacy breaches exist. And so along came differential privacy, and differential privacy is this nice sort of stability constraint on algorithms. And if you sort of squint at it, and people have actually done a lot more than squint at it, you can actually construct a privacy guarantee out of it, right? All right. And in fact, the reason why differential privacy is really, really nice, and these are things that, so when you go to a practitioner and say, you should use differential privacy, and they're like, why shouldn't I just aggregate my data and release the aggregate statistics? Like, what's the big deal, right? And so I've always found it like the 3 points that are very useful to convince someone that they should sort of try to at least think about differential privacy. So one is basically the fact that differential privacy is a property of a privacy-preserving computation. It's not a property of the output, right? What is the nice thing about that? It basically says that algorithms can't be reverse engineered. And I'll come back to this point when I describe work with the census data. The second thing is composition, and we've talked a lot about composition. It basically is that now when you do multiple releases, you have a way to reason about privacy before you don't have a way of reasoning about sort of disclosure and privacy in that case. And finally, sort of you can also talk about how this definition sort of bounds an individual's privacy risk despite sort of adversaries who sort of have some side information. Okay, and this is a little more nuanced. All right, so you had a decade of research, and you had some very sort of important practical deployments, particularly the US Census Bureau with Google and Apple and so on, and Yahoo and some others that were mentioned yesterday. But still, there is a big challenge in sort of taking all of the beautiful theory and algorithms that we have and actually deploy it in the practice. And a couple of important sort of points to note is that every one of these deployments actually have been led by sort of teams of experts. Right? This is not going to scale, right? We need sort of people who are not necessarily PhDs or professors in differential privacy to actually go and do the stuff, right? The supporting technologies in all of these deployments are not necessarily extremely transferable, and there's virtually no systems or software support for privacy non-experts to be able to do this stuff. Okay? So our goal is really to sort of take all of this sort of beautiful theory that we have, and in addition to sort of doing deployments, try to build some system support that is sort of transferable across different deployments. Okay? So in this talk, I will talk a little bit about sort of going from theory to practice and sort of get some learnings from there and sort of talk a little bit about some of the systems that we're doing. I may not get to the second part, but I'll try to sort of give you the high-level ideas. All right. So the first point is basically the following, right? You want to show that differential privacy is, it's feasible to do a differential priority computation in place of an existing sort of traditional data analysis, and show that you can actually do something good, like you can get provable guarantees of privacy with little loss in utility, right? And in this first part of the talk, I'm going to sort of talk about how we looked at this in the context of Census Bureau data and show that yes, you can do it in certain settings. Okay. So what is the setup here? So there was this product where the Census Bureau is currently sort of releasing data, right? So they already have algorithms in there. Why should they change it? Well, the main pitch here was that the current algorithms with data release not only had no provable guarantees, but they actually had their parameters had to be kept secret, right? So go back to World War I. How many of you have heard of Navajo talkers? So basically, yeah, right? If you know exactly what algorithm was used to encrypt, then in this case, you can just reverse engineer everything, right? So that's not good. So you want to actually have algorithms that are in the public domain where anyone who has expertise can look at it and say, yes, this is a secure or private algorithm, right? So that was sort of the key pitch that we made. Okay? So in this work, what we did was And then the other thing we did was, rather than just sort of say, OK, you use differential privacy, we started with saying, OK, let's look at the relevant US law and their interpretation and try to sort of formalize those mathematically. And then based on that, get a definition that looks like differential privacy, and then sort of add noise to the statistics that they want to release and release those statistics. OK? And the nice side effect, I mean, we were just doing this exercise just to sort of understand really what it takes to do this, but the nice side effect was that for a significant number of their analysis they're interested in, we had comparable or lower error than the current non-private methods. Okay, this is joint with the work with my student and some folks at the US Census Bureau. All right, so what is this application? This application basically is called On the Map, which basically allows you to sort of get statistics about where people live, where people work, and some attributes about people and workers and so on. And they actually use it for some interesting applications. So one application is if a hurricane is barreling through the US, then they can actually track the areas where it is going through, sort of count how many jobs are affected, and then use that for resource allocation. Okay? So let's go back to the underlying data. When we talk about differential privacy, we talk about differential privacy in terms of there is a database which looks like a flat file, and you're adding or removing one row. Well, here you're not having a flat file. You actually have a database. You have multiple tables. You have multiple entities. You have entities like employers, employees, jobs. You have key constraints between them, and so on, right? So that should sort of hint to where the real challenge was in actually doing this deployment. Okay, so here's the underlying data. It's called LODES. It's collected by sort of piecing together many different sort of data sets from various state organizations. And the kinds of queries they want to answer are sort of counting queries over jobs, conditioned on, filtered by various attributes on businesses, various attributes on individuals, and so on. Okay? So now let's start with the law. The law here, the law regulating the release of this data is Title 13, which basically says that any publication should actually preserve the privacy of both the individuals and to some extent also about the establishment. The law itself is so short that it really didn't tell you anything about how you can mathematically formulate it. But then we went back to, I mean, they've been doing this for 50 years now, so they have a lot of sort of insight into how this law is interpreted in practice and what their beliefs about privacy are. So based on that, based on conversations with people and their email threads that talk about what is private and what is not private, we came up with these sort of constraints that essentially you don't want the existence of a job held by a particular individual must not be disclosed. You should not be able to tell whether an individual is in the data set or not, or if an individual is employed by employer 1 or employer 2. And you should be able to guard against informed attackers. Like, for example, a coworker in your business, in your company should not be able to tell something about you or your attributes. The existence of actual employer businesses as well as its types are not confidential, because essentially they had a census of businesses, which means they knew exactly every business. And these businesses sort of had physical locations. So therefore, the fact that it's there, you can just go there and check it is there. So you don't need to protect that. But on the other hand, you have to sort of protect the data on the operations of a particular business. This is a little vague because, I mean, you already know whether a business is large or small. You know that Microsoft is huge. You know the small business is small. What you want to sort of protect is sort of the exact count on the number of people who work there, because that exact counts may leak some competitive advantage to others. So yeah, so basically we said, OK, can we use differential privacy here? As I pointed out, it's non-trivial, right? So basically there's no flat file. You need to start thinking about which entities should do this database have to do different. Do they different one employee, one employer, something else? We can apply a variant of differential privacy to this, and I'll come back to this later. But we wanted something sort of more closely tied to what they actually wanted in their standard policies, right? And the other question, of course, is how does DP and its sort of variants compare to the current interpretation of the law? The interpretation of the law talks about attackers, whether they're informed or not, and what they say certain things are secret, certain things are not. How does sort of various notions of neighboring databases apply to that, right? And so for this, we went back to some older work we had done in terms of Pufferfish, which is an alternate way of thinking about privacy, and it's a generalization of differential privacy. So in this Pufferfish framework, we sort of think of privacy define privacy in using three concepts. One is basically what is being kept secret, and you can think of these as sort of pairs of mutually exclusive statements, like is an individual in the database versus an individual is not in the database, or does an individual have cancer versus does the individual have diabetes, and so on. We also talk about adversaries, which are basically the set of data evaluation scenarios for the database. You can think of these as adversary priors. And you enumerate a set of them, and you want to show that across all of these adversaries, these adversaries are not able to distinguish these sort of discriminative pairs of secrets. And then your privacy guarantee is that every adversary in your set of adversaries can't tell apart a pair of secrets any better by observing the output of your computation. And so more mathematically, what kind of guarantee you get is basically that for every output that a mechanism generates, for every pair of sort of secrets, person 1 is in the table versus person 1 is not in the table, for example, and for every adversary with some technical conditions, the posterior odds of the adversary thinking S versus S prime is true should be close to the prior odds of the adversary thinking that S and S versus S prime is true. Okay? All right. So the advantages here is that it allows, so it generalizes differential privacy. Differential privacy is a instantiation of that. It allows you to define privacy more generally in terms of sort of secrets rather than just records. So you can extend it to sort of cases where you have multiple tables. You want to protect different properties of these tables. And you can tailor it to sort of this set of discriminative pairs. And so therefore, you can carefully associate it with like the kinds of adversaries and secrets that people care about. Okay? So yeah, so basically, we use this framework, and we were able to set up a set of discriminative secrets, a set of data evaluation scenarios, and we were able to come up with a privacy definition that looked like differential privacy, but was appropriate for this setting. So this is an example of a mathematical formulation of one of these privacy requirements that came out of this framework. Okay? So yeah, so in the end, what we got was a definition that gave differential privacy type guarantees for all employers. Okay? So an algorithm output is insensitive to adding or removing one employee record. You got appropriate privacy for establishment. It's not like adding or removing an establishment, but sort of changing an establishment's value, number of workers to some within some fraction. And it satisfies some sequential composition. So you could do, it has a nice graceful degradation in privacy, both in terms of multiple releases and sort of in terms of groups as well. Okay? So now I won't talk about algorithms. The algorithm design part was fairly straightforward here, but I'll come back to that in a few slides. So the question was, OK, let's design some simple algorithms, something based on Laplace mechanism and smooth sensitivity. And then we asked, OK, what is the utility like? So for utility measurements, what we did was we basically said, OK, let's ask some queries. So in this case, we asked two kinds of queries. One query was the marginal counts over establishment. So you can think of this as a set of 33,000 counts released simultaneously. And also, we also did some ranking experiments that I won't show today. And the utility cost we measured was basically the error introduced by our new algorithm that satisfies our sort of provable guarantee of privacy over the error of the current algorithm. They already have an algorithm, which was this sort of this Navajo-Tucker's kind of an algorithm. And if this ratio is close to 1, then that's great. You get provable privacy, and you get sort of utility that is comparable to the current system. And so this is a graph. So in this graph, there are 3 panels. Each panel is a different algorithm. The first algorithm is a simple application of Laplace mechanism. The last 2 are something related to smooth sensitivity. I'm not going to go into the details. This is the utility cost. So 1 means here exactly the average cost is the same in terms of error. This is higher than the current algorithm. This is lower than the current algorithm. And the y-axis in each panel is the privacy. Again, this is more privacy, and that is less privacy. Okay? There are many lines. So note that we have 2 kinds of entities you're protecting. You have employees, right, who have to have this differential privacy type guarantee. We characterize that as an epsilon. And there are employers. And employers, you can also, they have a different kind of privacy guarantee. It's not about whether employer is in or out. It's to the amount to which you can't sort of tell exactly what their value is. So therefore, there are 2 sort of privacy parameters here. One is this epsilon, another is a combination of epsilon and this factor alpha here. So basically, in all of these cases, if you look at any point here, in all of these cases, the individuals get the same amount of privacy. And what you vary is the amount of privacy you get for the establishments or the employers. And this is less privacy here and more privacy here for the establishments. Okay? So yeah, so what we found was that for some values of epsilon greater than 1 and alpha less than 5%, the utility cost was at most a factor of 3 across all of these algorithms. In some of these algorithms, if you allowed for a small probability of failure, in this case, you could get things that are much better. Okay? We actually designed an algorithm that is sort of differentially private. So think of it as doing differential privacy on establishments. So you hide the presence of whether an entire establishment is present or absent in the data set, and that automatically guarantees all of these privacy requirements. We designed the algorithm. We actually came up with a graph showing its line. And then when it came to publishing the paper, we said, OK, we're going to publish this. And they said, wait, we have to do a census internal review of the results before publication. They did the review, and then they came back and said, you can't release the differential privacy line. I was like, why? So it turns out what you're reporting here is the error of a differentially private mechanism over the error of the current mechanism. And the algorithm we used was something related to sort of truncation. If an establishment size was large enough, then you sort of throw it away, and otherwise you keep it. And for a lot of the lines that we drew, it turned out this ratio of error, from that you could actually infer properties of the original mechanism, which are supposed to be kept secret. And so therefore, the only thing we could report was this. Okay?
That sounds like more careful thinking was going into the analysis of your paper than of the outputs of the original.
Yeah, exactly. Precisely. Precisely. Yes. Okay? So there's another reason why, I'm sorry?
Sorry, I was going to say to Adam, but that's an improvement, actually.
So that's another motivation for why you want your algorithms to be public. You don't want to hide behind the secrecy of your algorithms. So that was a nice anecdote there. Okay? So yeah, so basically the first question that we all tried to answer here is like, can you sort of move from theory to practice? And we showed here that yes, we can, but let me sort of highlight a few sort of takeaway points, right, when you go from theory to practice. The first challenge that we faced here, and this is something that was more eloquently addressed by Alexandra yesterday, was like, you want to bridge policy and math, right? These guys, they talk about policies of privacy, whether you go to like a company and they're worried about GDPR, you go to Census Bureau and they have these policies on data sharing. Like, you want to be able to somehow bridge policy to math. And I think there's a great start in Harvard on trying to start thinking about this. And I think more of us have to try and engage with policymakers and see really how we can bridge this gap in ways that people outside the differential privacy community can understand the kinds of guarantees, the need for differential privacy, and can understand the kinds of guarantees that we give, right? The second challenge is more technical, is data is relational, right? And a lot of the work that we've done assumes either data is a flat file or data is a graph, right? But those are sort of two extremes, right? You have a larger space in between. And what effect does it have? I mean, it basically, you need to start thinking about privacy for different types of entities. You don't have a single entity here, right? You can have many different entities, each of whose privacy has to be guaranteed. You can have constraints between these tables. You can have things like functional dependencies, foreign keys, inclusion dependencies. And you may think that one of your tables is sort of doesn't have any sensitive information, but then because of these dependencies, it could become sensitive. So for example, I was talking to some folks at Honeywell who have this huge IoT infrastructure. They said, I have a light switch that tells me at every point of time the following data record, which is the location of the light switch, the time point, and whether it is on or off. What is privacy there? I mean, there's no individuals in there. But in really, the reason why you need to talk about privacy there is because this bulb becomes on or off if it detects a person, right? So in reality, there is a bigger underlying table, and this is just a view of that, right? So you need to sort of understand how these different sort of data that you're collecting relate to each other, and you need to sort of think about privacy more carefully in that space, right? You can talk to my student She/Her, who knows a lot more about constraints and databases than me, so please talk to her. Okay? The third big challenge is basically algorithm design. And this is a very nice quote And it basically says that without exception, ad hoc, the use of these technologies are ad hoc, cumbersome, and difficult to use. Turns out this is not a quote about differential privacy. This is a quote about databases in early 1970s by Turing-Arduino E.F. Cod. But it's the resemblance is very striking. We are exactly at the same time point where using these technologies is extremely, extremely hard, right? And so really what we need to start focusing now is moving all of the stuff that we know in theory and the deployment to build systems that are more easy to use for sort of data analysts so that we can scale out the building of differentially private deployments. And we need more and more deployments so that we can understand what is possible and what is not, and how to sort of apply all of this technology to real-world systems. And so in the last few minutes, I'm just going to sort of outline a high-level vision. So the vision is basically that we've given a task specified in some high-level language and a privacy budget. And again, there's a star there because we need to sort of rethink what privacy budgets mean. Synthesize algorithms to complete the task with near optimal accuracy and with differentially private guarantees, right? And you want to do this in practice. And I mean, so one example could be you're given a relational schema and a set of SQL queries. You want to answer all of these SQL queries jointly under a common privacy budget. And so the state of the art in this space is that there are systems that try to answer, for example, SQL queries, right? But they're far from utility, right? They answer one query at a time. And there are lots and lots of sophisticated algorithms that achieve near optimal utility, like K-norm mechanism and others, for specialized query types, like linear queries on single tables and certain queries on graphs. And so the challenge for a practitioner, a non-expert practitioner, is that, A, you need to cast problems in terms of these specialized queries, right? Your algorithms usually assume some special representations of the data. It's not like a relational set of tuples and a schema constraint. It's like usually it's like a vector domain over the entire full domain and some sort of matrices over that. There are no standard implementations of algorithms, and algorithms for achieving the best utility can actually depend on the data set and the privacy parameters that are used. And this makes this whole space, even though there exist algorithms in papers, it's extremely hard for them to sort of use it. So depending on how much time I have left, I will 3 minutes. OK. So our vision is to build this system. We call it System P. It is, for those who, most of you are not database people, the first database system was called System R. So we're trying to call it System P. And the high-level idea is that you want analysts to specify only at a high level what needs to be done. You know, either a set of SQL queries or a high-level description of the program they want to run. And we want to automatically synthesize a differential private algorithm for them. Okay, and I'll talk a little bit about some recent work we have done on sort of on differential private algorithms for answering linear queries. So linear queries are a subset of queries on sort of single tables that encode a large number of sort of very important statistical tools like one-dimensional range queries, marginals, predicate counting queries, and so on. There's a lot of literature on sort of optimal mechanisms, both in theory and in practice for this space. So for example, in the census, a very large fraction of them are just linear queries on a single person table. And so the challenge basically is that we've made steady progress on algorithm quality. This is basically showing you for the same epsilon, these different algorithms, as time has progressed, have sort of used that epsilon better and better in getting better accuracy for the same epsilon. But then the story is really nuanced because different papers say one algorithm is better than the other. So in this case, in this paper, it says blue algorithm is better than the green algorithm. In that paper, the green algorithm is better than the blue algorithm. It's not a fault of the papers themselves. It's basically that the algorithm performance is data dependent, right? So if you use a different data set, we do a slightly different setting, so therefore, you do need, there is no sort of one algorithm that rules them all, and which is what we found in a recent benchmark study that we did. So I'm going to sort of just talk about one quick thing. So algorithm design for a new task is a big challenge. And so here's how an algorithm usually looks. So this is an algorithm that computes a CDF of salaries for males in their 30s. And if you sort of break this algorithm down, so first of all, the thing that I don't like is that in most of these algorithms, actually the access to the input, the pre-processing, and the input creation is sort of muddled up with the DP logic itself. And ideally, they should be sort of isolated on two different places, right? But if you think about these algorithms, you can break them up into small, sort of higher level plans over operators. So the first part is sort of data transformation. The second part here, you're trying to actually take your data and reduce it in some data-dependent manner. The third part here is like query selection. I want to compute the CDF. I won't actually measure the CDF query workload because it has high sensitivity. I'll use a different workload. And then I will measure that using Laplace mechanism. And then I will use inference to infer the original queries based on these new queries. And this is what you need to do to actually compute a CDF with reasonably good accuracy in practice. Right? And this is too much for a non-expert to be able to write. But then if you think in terms of these high-level operations, this makes sense. Like data scientists keep doing this in machine learning all the time. Right? They say, oh, I will use a data reduction, a dimensional data reduction operation. I will use some sort of feature selection and so on. Right? And so we have this system where we can write algorithms in sort of these high-level operator classes and instances. And basically, we can rewrite a lot of these benchmark algorithms. We can create new algorithms by just sort of composing these operators. And it has a lot of advantage in terms of code reuse. Improved operator implementations can improve many algorithms simultaneously. We can do planned rewrite rules. So given a plan, we can automatically rewrite it so that you can improve accuracy and runtime. And you can create new algorithms which get 10x accuracy improvement. And right now, like if you do a 10x accuracy improvement, that's a paper on its own. But actually, you just get it by sort of recomposing existing operators from existing algorithms. Okay? So to summarize, essentially our goal is to empower non-experts to be able to build differential private algorithms with little loss in utility. And I think what is needed is shift from theory to systems-oriented research. We need to build reusable system tools. And in doing that, there are still a number of interesting theoretical and system research challenges, and both in the context of relational databases and also in building systems. Okay, with that, I'm going to stop. Thank you. Everyone's hungry. Yes?
So for your employee scorecard, I mean, did you look at it as a bipartite graph?
Yes. That was that's how we did the differential private algorithm. Basically, if you think of it as a bipartite graph, and you can just do node differential privacy that is stronger than everything else. And then we got these differential private algorithms, but you were not able to release but they were uniformly higher error than the customized definition that we got. That's right. Yeah. Okay. Yeah.
So actually, just to in the context of the LODES work, how it's hard enough to settle on epsilon. How did you settle on alpha? I mean, did you?
Yeah, it turns out they have thought about this for 10 years, right? They had a policy for,
a policy that basically specified alpha.
Yeah, they had a policy, and I'm not privy to what their specifications are, and that's not my job. My job was to just give them the curves and let them choose based on that. But basically, they already had a way of thinking about both. I mean, they had a way of thinking about privacy in a different context for individuals and establishments, and so it sort of made sense for them to think about it. They said, this came from them.
And on those graphs, smooth Laplace refers to sort of Laplace with the
smooth sensitivity. Yeah. That's right. Yeah.
All right, let's thank Ashwin again.